I guess we'll just jump right into it. So this is the ARES 6 test stand, also known as Project Atlas. Let's see here. This is our team. Right, today we have Daniel McCulley, who's the electrical system lead, Emily, who is the software system lead, and Moore, who is the sensor system lead. Those are our technical roles. The administrative ones are more for Dr. Branham. So this is the blueprint. This is modeled here as SED's Colossus test stand, which is kind of the inspiration for this test stand as a whole. So we're using them as a heavy influence for how we design and build ours. The purpose of the test stand is to create a rocket engine test stand that can test both solid motors and liquid engine rockets. This test stand is going to be used by future ARES teams and future ARA teams to test their rockets and engines. These are our mission objectives. So we're just stating that the test stand shall allow engines and motors to be tested at full flow, operate remotely from a safe distance of 200 feet, withstand 1,500 pounds of thrust, which includes a 50% safety margin. And it'll adhere to all the state, federal, local laws and regulations, and be able to test both solid motors and liquid fueled rockets with a built-in emergency shutdown feature. So success criteria, we define success as a completed design, construction will be underway and hopefully completed, successful testing of each subsystem, complete documentation of our design process and how to use the test stand, one static fire at the end of the year, and then the ARES rocket will be able to integrate with the test stand. This is our work breakdown structure. Each of these, so we just have the test stand system, electrics, structure, and all that modeled here. This is our project schedule. This is barring any like setbacks or delays, but we'll have our CDR coming up here soon with Dr. Branham for senior design. And after or before that, we are hoping to be able to order and receive all of our parts and hardware so we can get going right when the spring semester starts. So this is structures. We're planning on using a utility trailer as our base structure. It's from SLE Equipment, and it's pictured here. The dimensions in the layout aren't updated because we are working with 6.4 feet by 18 feet now instead of 8 by 14. But here is a general picture of how the layout of the test stand is going to look, with the tanks in the back and the engine interface and thrust takeout are going to be on the opposite end of the trailer, off the back of the trailer, and we'll have the power supply and nitrogen tanks closer to the oxidizer and fuel tanks. Like I said, it'll be able to take 1,500 pounds of thrust with a 50% margin built in. It'll be able to run capable or independent of a rocket without the tanks and plumbing from a powerhead system. All structures are modeled using SolidWorks and tested using SolidWorks. So the difference between Colossus and our stand is that we're going to be thrusting straight downwards as compared to their 10-degree upward angle, or downward angle, I should say. This was decided, Dr. Branham recommended that we don't use the 10-degree thruster because it complicates things, and he was more comfortable going with the 90-degree straight down. So we will be thrusting off the back using this structure in the bottom left corner. And then the model on the right is our tank support system, and this will be built using 80-20. So this is just stating how we're going to test the structure and the flow through the pipes. A lot of testing on ANSYS structural, thermal, and vibrational. We're looking to maintain at least a safety factor, or a safety factor of at least 2 throughout the whole system. And then there'll be a thermal analysis to simulate during a hot firing of how the stand will be able to make it through, and then the flow integrity, and make sure that the feed lines are going to be able to take it. And then I'll pass it off to Maura.
Can you guys hear me?
Yeah, I can hear you.
Okay. So I'll just talk a little bit about our data acquisition system. So we're going to be getting a compact controller called a CRIO from National Instruments. And so that'll be used with the LabVIEW software to control the sample rates of the data coming in and to convert it into the digital data. So we're going to be getting these analog input modules for the thermocouples, the voltage, and the bridge and strain. So the thermocouples will be going into the thermocouple input. The ambient conditions and the pressure transducers will be connected to the voltage input, and then the load cells will be connected to the bridge strain input. And then that's on the blue device is how it'll be attached to the panel. So you can go to the next slide, Tyler. So this is what our P&ID is looking like right now. So you saw on the previous slide that we have 3 load cells, 14 thermocouples, and 9 pressure transducers. So we'll be using those instruments to measure the thrust of the engine, the tank volume and pressure and temperature, as well as the pressure and temperature across these choked orifices on the feed lines so that we can measure the flow rates. So you can see that we have the purge system as well as the pressurant tanks, and then the fuel and oxidizer, and the various ball valves and check valves that we'll have. And then we'll also be protecting our instruments from the cryogenic temperatures using insulation for the thermocouples as well as stainless steel tubing for the pressure transducers. Next slide.
The software system has 4 main requirements for it. The first one is to provide remote operation of the test stand from a minimum distance of 200 feet. This communication will be done by a cable running from the test stand to the operator stand, with a wireless system acting as a backup. The second is to monitor and report the health and status of the test system. We will be comparing the data gotten from the sensors to make sure that every sensor is reporting the correct data. And it will also alert the operator in case of a failed sensor or if the test exceeds testing boundaries. The software will also store all data from the test stand. This data will be used to provide analysis afterwards. And finally, the software will execute emergency shutdown procedures if the conditions are met. The figure on this slide displays the basic model of the software system, primarily the communication between the test stand and the operator stand, and the main functions needed to meet the requirements. Next slide.
All right, so here's the power budget. Colossus had 2 separate voltage rails, but we'll only be using 1 as we don't need compressors, and that's what they use their high voltage AC rail. So we'll have 1 low voltage DC rail that will be supplied by an onboard battery. The main thing is just making sure that there's enough amp hours and enough power for the power requirements. This is basically everything we're gonna need. There might be like some random resistor or some random other component that we need to add in here. So the batteries we'll be looking at will be a bit larger than just 10.8 amps and 215 watts. But we'll be using, everything has a 24 volt option except for the microcontroller. And you're not gonna find a 24 volt microcontroller just because of how small they are. So yeah. The valves, there's 8 of them. They will be the DC valves, and then an LED tower is just there to make sure that we have a visual that everything is running good. Besides also getting the data on it. So if we're getting, say, faulty data that looks good but is actually bad for some reason, we can just have a simple indicator just to know that it's on. But that would be a very bizarre scenario if you would ever actually need that. Next slide. This is how everything communicates with each other. There is one slight change. The mini computer, because LabVIEW can now be done on the DAC, that's basically being absorbed into that component. So you can basically just treat it as if the mini computer just isn't there. But there will be two terminals in the operator stand, one for receiving data and then one for actually controlling it. Those will have to be done separately just because one, doing that and under one person will be a lot of work for it, but also you want to have direct control over the microcontrollers. So if there's a failure of the DAC, you won't be able to still control the test stand. And you also can't run data through the microcontroller and through the test stand just because of how much data there is. That'll be a lot of data that you're passing through. The actuators is all the valves and then all the lights, and then DAC and sensors are subsystems. So yeah, next slide.
So this is for our tanks and propellant feed system. We're looking to get 2 cryogenic rated pressure vessels around 2,000 psi operating conditions. Each tank is going to in order to measure the level of the tank during a test, our plan is to have several thermocouples attached directly to the metal and then coated around with a layer of insulation as a way to help measure the tank level. The feed lines we're still looking at those. We are debating and going through a trade of ordering them directly or getting stainless steel and insulating them ourselves. That's yet to be determined. The stand is going to use ball valves to control the flow of the propellant, pressure and purge gases throughout the system. And these ball valves are going to be toggled with pneumatic actuators. And that's similar to what Colossus used as well. This is a small breakdown of our budget. There's a better graph in the appendix of this, but basically the feed system has the most allocated to it for the tanks and the feed lines. That's a lot of work and money that goes into that. The structure has to be responsible for getting the trailer and the 80/20 whatever steel that we plan on using for the truss system. And then sensors and instruments, software and electrics kind of merge into one, but that's pretty straightforward. And then I built in a budget for maintenance that might come up along the way or after the completion of the test stand. And then this is just credit to people who have helped us. So ARA for making this the senior design team and helping us along the way, Dr. Branham, Spencer MacArthur for his donation, and then the other ARES 6 teams. Any questions?